In the following video, we're going to examine how to graph a continuous relation. The first example we're going to look at is y equals 1/2 x minus 3. We are asked to graph that equation, then determine the domain and range, and if it is a function, determine whether it is 1-to-1 onto both or neither. So the first continuous relation we're going to look at, y equals 1/2 x minus 3. This is a linear relationship. And the reason why we say it's a linear relationship is it follows our idea of slope-intercept form. Y equals 1/2 x minus 3 follows y equals mx plus b. So here our slope is 1/2 and our y-intercept is -3. So to graph it, I'm going to go to -3 on the y-axis, go up 1, right 2, and I'm going to follow that pattern. And then I'm going to flip it and do down 1, left 2 to continue the pattern. And these will be connected with a straight line. So that is going to be our graph of the relation y equals 1/2 x minus 3. Determine the domain and the range is the next step. So what you do when you determine the domain and range, for the domain, remember you look at the x values. And so we're going to focus left and right movement of our graph. These arrows on both ends tells us this goes all the way to the left forever, and this goes all the way to the right forever. There is no limit on my domain and range, so I'm going to say all real numbers. My range is the y movement, the up and down movement of our graph. So these arrows are pointing up, and it's going to continue to go up, follow that slope of 1/2, 1/2, 1/2 all the way up. Same thing, it's going to follow that slope all the way down. So there's no limit for our y values as well. So all real numbers. And now we're asked that if it is a function, and it is a function, it passes our vertical line test, determine whether it is 1-to-1 onto both or neither. So when I look at the following graph, I see that we do have one y value for every x value, and vice versa, every x value has one y value. So there is a 1-to-1 graph, but it is also an onto graph, which means it is both 1-to-1 and onto. Let's examine the next equation. Y equals x squared plus 1. So when I have y equals x squared plus 1, again, we're going to determine if this is a function. We're going to state the domain and the range, determine if it's 1-to-1 onto both or neither. So the first thing I'm going to do is I'm going to graph it. And this one, y equals x squared plus 1, since it has a degree of 2, we learned in Algebra 1 that's called a quadratic graph. So to graph this, I'm going to go ahead and make a table of values. -2, -1, 0, 1, and 2 for my x's. And I'll plug those in to find out the y. So -2 squared is 4. 4 plus 1 gives me 5. -1 squared is 1. 1 plus 1 is 2. 0 squared is 0. 0 plus 1 is 1. 1 squared is 1. 1 plus 1 is 2. 2 squared is 4. And 4 plus 1 is 5. And so now I'm going to plot these points at -2, 5, at -1, 2, at 0, 1, 1, 2, and 2, 5. And this, if we were to graph it, will be graphed with a curve. It'll be a U-shaped curve because it is quadratic. So now we need to figure out our domain and our range. Our domain, is there a limit to our x values? We would go all the way to the left. We would continue to choose -3, -4, -5, -6, same thing to the right. Our domain is all real numbers. But when we examine our range, the y values, we see that it does go all the way up. It's pointing all the way up. It's going to continue to positive infinity for our y's. But as we follow it down, the lowest y value that exists on the graph is right here at the y value of 1. So our y values are either 1 or larger. So that means your y values are greater than or equal to 1. And then is this a 1-to-1, an onto, both, or neither example? Well, if we take a look, we have the same y value for two different x's. At 1, we have a y value of 2. At -1, we have a y value of 2. At 2, we have a y value of 5. And at -2, we have a y value of 5. So we have a y value that is shared between multiple x's. The idea of that horizontal line test, it crosses twice. And since we have a y value that is shared across multiple x's, it is an onto function.